Okay, in today's lecture, we're going to start our Chapter 12 material on applications of the derivative. And in this lecture, we'll look at the first part of the section 12.1 material on something called a local extrema. So to begin this section, let's ask ourselves, now that we have a lot of experience with finding derivatives, what does the derivative of a function f prime tell us about a function? So we know that the derivative can be interpreted as an instantaneous rate of change of a function, or as the slope of the tangent line to the graph of that function at a specific point on the graph of that function. Now, if we think about the derivative as representing a rate of change, as we've already seen a little bit in the previous chapter, that would mean if the derivative of a function is positive for every x in some interval, that means that the function f would be increasing on that interval. So that is, if we have a positive rate of change, the value of the function is becoming larger as we're changing the value of x, or as we're increasing x. So similarly, if the derivative of a function is negative for each x in some interval, that implies that function would be decreasing over that interval. And in the case that the derivative f prime of x would be equal to 0 for some x, or for every x within some interval, that means that the function f would be constant over that interval. That is neither increasing nor decreasing, but it remains constant. So as an example, let's consider these graphs that I've shown here. So looking at the graph in this left-hand plot, we can see that our function appears to be increasing on the interval from -infinity up until 0. The values of our function are getting larger and larger. Now, if we look at the slope of the tangent line to the curve at any point within that interval from from -infinity to 0, we see that the slope of our tangent line, which would be the derivative of our function f prime of x, is positive. And if we consider the graph of our function from 0 to infinity, we see our function starts to decrease. And if we consider the slope of the tangent line to the curve at any point within that interval, we see that the slope of our tangent line is negative. So that is, the derivative f prime of x is negative. So here we could say that our function would be increasing on the interval -infinity to 0 and is decreasing on the interval from 0 to infinity. Now we have a similar interpretation for this left-hand plot. So if we follow the graph of our function from left to right, we see initially it appears to be increasing on the interval from -infinity up till x equals 1. And then it starts to decrease on the interval from 1 to 2. And then from 2 to infinity, our function begins increasing again. And this can be characterized by looking at the derivative. If we consider the slope of the tangent line to a curve on the intervals of increase, we see that our slope is always positive, whereas on the interval from -1 to 2, the derivative, which is the slope of our tangent line, is negative. So we can use the derivative of a function in order to determine where a function is increasing or decreasing by determining the sign of our derivative within a given interval. Now, when we consider the points where we were changing from increasing to decreasing, say when x was 0, or when x was -1 or +2 on this graph, we notice that those points where our tangent line is horizontal, or where the derivative is 0, are the largest and smallest values of the function close to that point. That is, it looks like our function is, or the graph of our function is sort of peaking out or bottoming out at those points. So these points where we change the sign of the derivative might indicate where a function has its maximum or minimum values, and we'll explore that in much more detail throughout chapter 12. So these points where our derivative is equal to 0 are given a special name. So a little terminology here. If f is a function, then any value c for which f of c is defined, so some value x such that our function is defined there, and either the derivative of f evaluated at c is 0, or the derivative of f at c does not exist, is called a critical value of our function. And the corresponding point, f of c, on the graph of our function is called a critical point. So for instance, in our figure above, the point where we had a 0 for our derivative was at x equals 0. We would call that a critical value. And the point on our curve, it appears to be 0, 2 here, this point, is called a critical point. So these critical points are going to be the candidates for where we might have a maximum or a minimum value for our function. Now we notice that part of the definition is that we have a critical value if the derivative is 0 or the derivative does not exist. So why do we care about points where the derivative does not exist? Well, let's suppose that we're looking at the graph of the absolute value function. So absolute value of x has a graph that looks something like this. And we can see that its minimum occurs at 0. And at that point, we have a corner in the graph of our function. That is, the absolute value of x is not differentiable at 0. The derivative does not exist. So these points where our derivative is 0 or does not exist are going to be candidates for where our function has a maximum or minimum. So summarizing our discussion about the derivative, or the sign of the first derivative, we now have a method to determine where a function is increasing or decreasing. And this is known as the increasing or decreasing test, which says the following. In order to find the intervals on which a function f is increasing or decreasing, we're going to perform 3 steps. The first step is to find the derivative, f prime, of our function. The second step is to find all of the critical values of our function. So those are the values of x such that the derivative would be equal to 0, or the derivative does not exist. And then in our third step, we would determine the intervals on which the derivative is either positive or negative by choosing test numbers in each of the intervals determined by these critical values. So the critical values that we find in part 2 will partition the real line into these little subintervals, and we're going to determine the sign of the derivative in each of those subintervals, and that will tell us whether our function is increasing or decreasing over that interval. So in particular, as we had mentioned above, the function f is increasing on the intervals where the derivative is positive, and is decreasing on the intervals where our derivative is negative. So now that we've discussed this concept of how the derivative relates to where a function is increasing or decreasing, let's look at some examples. So in this first example, we're asked to find the intervals on which this function, f of x, which is a polynomial, is increasing or decreasing. So for the increasing, decreasing test that we just described, our first step is to find the derivative of our function. So let's start by taking f prime of x. Now here we just have a polynomial, so it's easy to differentiate using the sum difference rule. So our first term would be 12x squared minus an 18x to the first, and then minus 12. So this is our derivative of the function, and our second step is to find the critical value. So that is determine where this derivative is equal to 0 or undefined. Now for the function that we have here, our derivative is a polynomial, which is defined everywhere. So the only critical values we would have are values for which this derivative is equal to 0. So we want to solve this equation for x, and I notice that each of the coefficients here is divisible by 6. So if I were to factor out a 6 from each term, I'm left with a 2x squared minus 3x minus 2 is equal to 0. So factoring that quadratic, we have 6 times 2x plus 1 times x minus 2 is equal to 0. So we have two options. Either this first factor is 0, in which case x is negative 1/2, or this second factor is equal to 0, in which case x equals 2. So negative 1/2 and 2 are our critical values. And let's see how we can use these to determine where our function is increasing or decreasing. So if we think about a number line, let me say the following. Consider a number line representing the domain of our function here. So say just the x-axis. And we found two critical values at x equals negative 1/2 and at x equals positive 2. So these two critical points divide the real line into 3 subintervals, everything from negative infinity up until negative 2, everything, or negative 1/2, everything from negative 1/2 to positive 2, and everything from positive 2 to infinity. And we need to determine the sign of the derivative in each of these subintervals. So how can we do this? Well, within each of these subintervals, we can choose some x value and evaluate our derivative f prime at that value. And whether we have a positive or negative value will tell us whether our function is increasing or decreasing. So for instance, in our leftmost interval from negative infinity to negative 1/2, I want to choose some value of x to plug into my derivative. So typically we try to choose integer values. Those are whole numbers, so that evaluating our derivative is a little easier. So choosing the first whole number less than negative 1/2, I might use negative 1. And if I evaluate my derivative, f prime, at x equals negative 1, well, let's see what sign we have. So substituting negative 1 into our derivative, we would have 12 plus 18 minus 12, which leaves us with 18, which is, of course, positive. So since our derivative is positive at negative 1, we know that our derivative will be positive everywhere to the left of negative 1/2. Now to indicate that on my number line, I'm going to draw a little direction arrow, which is increasing. That is, as we move from left to right, it's moving upward. So I know my function is increasing on that interval. So let's consider our next interval from -1/2 to +2. So choosing any number I want in between these, an easy choice might be 0. And if I evaluate my function f prime at x equals 0, I have -12, which is of course negative. So that means my function is decreasing on that interval, and to indicate that on my number line, I'm going to draw a little directed arrow which is decreasing as I move from left to right. And then in our last subinterval, everything from 2 to infinity, I want to choose some x value as a test value. So a good choice might be 3, or any other number greater than 2. And if we evaluate our derivative at 3, we end up with a value of 42, which is positive. So on the interval from 2 to infinity, our function is increasing, which we can indicate with a little upward pointing arrow as we move from left to right. So in summary, we would say that our function is increasing on the interval from -infinity up to -1/2, or from +2 to +infinity, anywhere that we had these little increasing arrows on our number line. And the function is decreasing everywhere else. So in this case, from -1/2 to +2. So this example illustrates how that increasing decreasing test works and what this derivative can tell us about our function. Now, we had mentioned in the first part of our discussion on increasing and decreasing that these critical values might be able to, where we change from increasing to decreasing, might tell us whether or where our function has its largest or smallest values. So let's introduce a little terminology as reference for those largest or smallest values. So here, let's define the following. Say that f is a function which has a domain capital D, and that domain contains the number c. So our function is defined at c. So we would say this function f has a local maximum at c if f of c is greater than or equal to f of x for all x in some open interval containing c. And the value f of c is called the local maximum value of the function over that domain. So geometrically here in the figure that we have below, a local maximum might be a point like this one. It looks like maybe the point 1,5. And we would call this point a local maximum because the value of the function at 1, which appears to be 5 here, is the largest value of the function within a little open interval containing x equals 1. So notice that all of the other values of our function in that interval are smaller than the point we have up here at our local maximum. So we would say, again, that f has a local maximum at, in this case, 1 in the picture that I've given here. And the local maximum value is the value of the function at that point. In this case, it looks to be 5. Now, similarly, we could define a local minimum. So we would say a function f has a local minimum at a point c, or at a value c, if the value of the function at c is less than or equal to all other values of the function f of x for every x in some open interval containing c. and the value of the function at c, that is f of c, is called the local minimum value of the function. So on the graph that I've given here, it looks like we might have a local minimum at the origin, 0, 0, and at the point 3, and looks like maybe negative 27 or something like that. But we see here that in a small interval centered at 0 or containing 0, this function appears to have its smallest value within that interval at the origin, 0, 0. Or similarly, for a small open interval containing 3, it looks like the smallest value of our function within that interval is occurring at this point down here. So we would call these values local minimum values. And we see from this example that it's possible to have more than one local minimum. Now together, we would say that the function f has a local extremum at c if it has either a local maximum or a minimum at that value c. And the local maximum and minimum values of the function are called the local extrema of f. All right. So let's look at an example where if we're given the graph of a function, we need to determine the location of the local extrema for the function whose graph is shown. So here we have the same two plots that we started with on our first page. And we see in this left-hand figure, it appears that our function has a local maximum at x equals 0, and the local maximum value appears to be positive 2. So here we have a point positive 2, a 0 positive 2, which would be a local maximum. And it doesn't appear that there are any other local maximum values or local minimum values here. It doesn't look like our parabola opening downward has any minimum points where it's bottoming out. Now in our figure in the right-hand plot, let's start by identifying a local maximum value. So it looks like maybe when x is negative 1, our y value is 2. So this point, negative 1, 2, would be a local maximum, where 2 is the local maximum value. We would say that the local maximum occurs at x equals negative 1, and the local maximum value is 2, the actual value of the function at that x value. Now we would, in this example, also have a local minimum. It looks like at x equals 2, our function is bottoming out within that interval. And it looks like our y value would be maybe negative 1. So this point 2, negative 1 on our graph would be a local minimum. So again, we would say that the function has a local minimum at x equals 2, and the local minimum value, the actual value of the function at that point, is negative 1. So here, introducing this terminology and seeing how we could identify local extrema if the graph of the function is given. So let's consider how these local extrema might be located. So typically problems of interest in applications are finding the maximum or minimum values of a function. Say, for instance, in business, maybe maximizing profit, minimizing cost, minimizing the time it takes to manufacture a certain amount of goods, maximizing, say, productivity. So we're interested often in determining the extreme values of a function. So we're looking for those points where we have a local maximum or minimum, and how can we find them? So this theorem gives us a connection between local extrema and critical numbers. So this theorem says if a function f has a local extremum, so that is either a local maximum or minimum, at a point x equals c, then c must be a critical value of that function. So if we have a maximum or minimum at some point, or at some x value, that value of x must be a critical value. That is, either the derivative is 0 or our function is undefined at that point. Now, a word of warning about this theorem, a common misconception is that if a function has a critical value at some number, say x equals c, then there has to be a maximum or minimum at that point, but that is not true. So as a counterexample to show why that's not true, we'll consider the following. So just because the derivative of a function is 0 at some value c, that does not necessarily mean that the function has an extreme value there. And the counterexample that we will consider is the function f of x equals x cubed. Now we know the derivative of that function, f prime of x, would equal 3x squared. And so if we evaluate the derivative at x equals 0, we would have a 0 value for the derivative. So 0 is a critical value for that function. However, looking at the graph of f, it does not have a maximum or a minimum at 0. So let's think about what the cubic function looks like. If we sketch the graph of y equals x cubed, it looks like the following. So we can see from our graph that at 0, we do have a horizontal tangent line. So here f prime of 0 is 0. However, by inspection, we can see that that is not a local maximum nor a local minimum. So these critical values are going to be candidates for where we have a local extremum, but do not always guarantee that we will have an extremum at that point. So let's look at some examples where we'll find the critical values of a function, because those are the candidates for where we have a maximum or a minimum. So in part A, we have f of x is this polynomial function. And in order to find critical values, we need to consider our derivative. So here, f prime of x would be equal to 1x squared minus 2x minus 15. And once we find our derivative, we ask ourselves, is there anywhere that it's undefined? Now this derivative is a polynomial, which is defined for all values of x. So the only way that we can get a critical value is if this derivative is equal to 0. So to solve for x, we can factor this quadratic as x minus 5 times x plus 3 must be 0. And so we find we have two choices. Either x is equal to positive 5 or x is equal to negative 3. So these would be our critical values for that function. These are the candidates for where we have a maximum or a minimum. Now in part B, we have f of x is 6x to the 2/3 minus 4x. So again, to find the critical values, we must first find our derivative. So here, f prime of x is equal to, let's see what we have from the power rule. When we pull down our factor 2/3 and multiply by 6, we get 4. And then we decrease the power of x by 1. We get x to the negative 1/3 power. and then minus the derivative of 4x is 4. Or rewriting this, we have 4, and then the x raised to the negative 1/3 is the same as dividing by the cubed root of x. So remember, when we have a negative exponent, that's the same as taking 1 over x to that positive power, and then x to the 1/3 power is the same as the cubed root of x. And then we still have our minus 4. So to determine critical values from this derivative, we ask ourselves, is there any point where this derivative would be undefined? And we see, because of this division by the cubed root of x, that we would have a derivative undefined at x equals 0. So that's going to be one of our critical values. Now, the other way that we can have a critical value is if our derivative is equal to 0. So let's see if we can solve this equation for x. So if I add 4 to both sides, I have 4 over the cubed root of x is equal to 4. Or dividing both sides by 4, I have 1 over the cubed root of x is equal to 1. So multiplying both sides by the cubed root of x, I have the cubed root of x has to equal 1. And then cubing both sides, I have x has to be 1. So our critical values here, listing them together, would be x equals 0, because we saw the derivative would be undefined there, and x equals 1. That's the value for which the derivative is equal to 0. So again, those are the candidates for where this function has a maximum or a minimum. So let's look at one last example. In part C, we have f of x is this rational function, a quotient of two polynomials. So to find our derivative, or to find our critical points, we have to find our derivative. So here, to differentiate a quotient of two functions, we have to use the quotient rule, which says we first differentiate the numerator. So we would have 1 times the denominator, x squared plus 1. Then we subtract the numerator, which was x, times the derivative of the denominator, which is 2x. And the whole thing is divided by the denominator, which was x squared plus 1, quantity squared. So simplifying a little bit in our numerator, let's see what we have. I've got an x squared plus 1, and then a minus. When I distribute my x, I have a 2x squared all over x squared plus 1 quantity squared. So grouping like terms in the numerator, I have 1 minus x squared, and I'm dividing by x squared plus 1 quantity squared. So to determine critical values, I would first ask myself, well, is there any value of x such that this derivative would be undefined? So we might suspect, because we've got a quotient, well, it's undefined if we have division by 0. But notice that our denominator, x squared plus 1, is always at least 1, because when I take the square of a number, it's always either 0 or a number greater than 0. So taking x squared plus 1, I would have something greater than or maybe equal to 1, but I could never have division by 0. So this derivative is defined everywhere. So the only critical points that I might have or critical values that I might have, are values such that this derivative is equal to 0. So here, if we set this fraction equal to 0, that implies that the numerator, 1 minus x squared, must be 0. We could multiply both sides by our denominator, x squared plus 1 squared, and when I multiply that by 0, I'm left with just the numerator is equal to 0. So 1 minus x squared is 0, which means 1 is x squared, and so x could be positive or negative 1. So these would be my critical values for that function. Again, those are the candidates for where this function has its maximum or minimum values. Now in this example, we've seen that these critical numbers are we've seen how to find critical numbers, and we've seen that they are the candidates for where our function has its maximum or minimum values. But how do we know whether a function has a maximum or a minimum at those values? And how do we know whether it's a maximum or a minimum? So that's what we're going to discuss in the next part of